Hey, what's up, guys? Welcome to my algebraic geometry lecture. And yeah, this is another exercise or another theorem, which is also important. So I want to make a video for it because you will use it in a simplification or other kind of results. And basically, this is the same as this comes from Cal, and this is one is Harshal. Okay, so hopefully I didn't spell it wrong. Okay. Basically, simple speaking is that you have morphisms, which are isomorphism. So let me just say this. So starting point is that you have two sheaves, right? If two sheaves, it's isomorphism as the isomorphism sheaf, then if it induces isomorphism on all stalks, okay? And or in Harshall's notation is that if you have F to G, morphism sheaves on top of unit base X, then finds isomorphism if only if induced map our stalks are all isomorphism for P belongs to X. Okay, and as I said, if you don't do the exercise in the algebraic geometry, then I guess that you will not learn anything. Okay, so this is why I want to make a video list. Hope you guys subscribe to my channel. Okay, yeah, so let's prove. So okay, so let's follow Harshon's notation, right? So we have this. So we want to show that phi is isomorphism. If phi p, phi p introduce. Oh, by the way, if you haven't seen my previous video, then you can check out that the morphism between the sheaf will induce a morphism between the stalks. If you don't understand why this is true, then you should stop video and go to my previous video to show. You should do the previous exercise to show that the morphism between sheaf will give you a morphism between the stalks. Okay, if IP is isomorphism for P. Okay, so obviously that the one direction is trivial, right? Because if they're same as isomorphism, then they will induce the same isomorphism on stalks, right? So these directions is trivial. So the difficult direction should be here. Okay. Let's say this is isomorphism for every P, and we want to prove that this guy is also isomorphism. Okay, so now let's start. Oh, the first one is injective. So injectivity is trivial. Probably not trivial, but you can use the another results that I previously proved. You can check out my another videos called more on stalks. You can check that video. In that video, that I think I proved results that if you start from F, right, and you take U, and then you go to like do the products. P belongs to U F of P, and then you go to G of U, and then you can go to the P belongs to U, G of P. And what in that video I proved that these two map are injective. Okay, and now you have induced on injective on this map, right? This map are injective, right? By this. So we are assuming that this guy is isomorphism. We want to prove that this red, right? So this map are injective, and then you can show that this map is injective. Okay, so proof is not difficult. How do we prove it? This is just the set theory results. So let's see. So if you have, let's say, A and B, right? Suppose they are different, and we want to prove that this will be different, right? So prove by contradiction. Suppose they are the same. So let's say this map are the same, so that this will be, let's say, phi, right? So it will be phi of A. Suppose phi of A is the same phi of B. Then this guy is injective, right? So that means that these results, these two will be different. Okay, these two are still injective, so that means that these two will be different. But then you suck, right? Because this guy is also injective. So the same thing cannot become the two different things, right? So this red one must be injective. So these two must be different. Okay. So it's very simple that this just a commutative diagram. Okay, so injective injective is simple. Okay, so it's simple to prove. Okay, so actually the difficult part in this proof is that surjectivity. Surjectivity it's very difficult, I think. It's very hard to think very hard to think how to come up with this. Okay, so let's go through this. So let's use this diagram, okay? Okay, so now we have this diagram, right? So let's say, so in order to prove the surjectivity, we need to prove that I need to choose a section. I need to choose the T of this G, okay, as a G of U, okay? And then I want to say that if I fix G of U to be T, I find element T of G of U, and I want to find the global section. So the problem is that how do you find this global section? It's somehow like you need to use the groupability of the sheaf, right? So proof idea is that I come up with this. I just choose T belongs to G of U. Now for all B belongs to U, right? Then let's write TP as a stalks, right? Or germs or stalks. Okay, so this TP just right. So I mean, I think everyone knows it, right? Just P, just take U. For all P belongs to U, right? Let's fix P. So you can take U, and then take G of U. Sorry, I take T. So this is the representative between in the TP, right? Since P belongs to U. Okay, so let's call it TP. So TP is stalks. Okay, TP is a stalks, right? So we know that phi P is surjective. So that means that what? That means that I can find SP, right? There's let's call it SP. So SP is also stalks at P, where there stalks FP, right? Because now we have FP to GP, right? So if you take a TP to be stalks, right? So now your T will goes to TP, okay? And then you want to find, oh, there's a guy SP, right? So so this is the proof idea is that you start from locally and then you try to glue them globally, okay? So we find a file SP such that phi PSP is TP. Okay, hopefully this is simple. Okay, so now SP, right? What is SP? I can write SP as this kind of form, right? So I can write SP as a VP. So VP is open set, right? And then there's a section. So let's write this this section is called S, bracket P. Okay. Okay. So now what? So now we know that okay, so from here that by the previous video or the induced map on stalks, right? This phi P. If I map this SP to phi P, then we'll get VP and then phi P and SP. Okay. So this tells me that phi P, SP, and TP are the same, right? But just my definition, right, are the same in GP. Let me just highlight this. Okay, so this means what? This means that they should be the same, right? They should be the same at the smaller open sets, right? So I can freely assume. So I can just simply assume that at smaller VP, so I could just say that I can shrink a VP to be very small, such that these two are the same. Okay, so simply speaking is that I can just force this is to be true, right? Because they are the same, so I can write as T and restrict it on VP. Because now they are the same in the germs, right? The same in the germs means that T restricted to VP as phi P map into as phi not phi P. This is phi. This is phi, right? Because this is in terms of germs, so this should be phi. Yeah, so in terms of the global section, so the shift induced map just apply the phi at the sections. Okay, so we have this. So we have phi SP equals to T restricted in VP. Okay. Okay, so now we have this. So now we are good, right? See, because we find some open cover VP such that the T and the phi sp are the same. Okay, so now we should use the gluing property, right? So let's write U. I know that U is covered by VP, right? Because for each P, yeah, I can take this. Okay, and so it's very beautiful that each T this section on VP always the same as phi sp. Okay, so we need to check that they are equivalent on their intersection, right? Okay, so it's very simple that suppose that SP and VP intersection are VQ, and let's say suppose this and these are the same. Let's say we consider their intersection for 2 points. This is Q. Okay, if they map to the same thing to call T, then what? Then since phi is injective, as we proved before. So we know that SP VP intersection VQ is SQ VP intersection VQ. Okay, so this tells you that their intersections are the same. So by the sheaf property, there is what? There is S, right? There is a S. Global section belongs to FU. Okay, such that S reduced to restriction on VP is just SLP. Okay, for this. Okay, so now you can find you already find the global section on the right hand side. Sorry, on the left hand side. Okay, so we have this global section. Okay, so the remaining, right? The remaining is to show what? Just to show that phi of S is just T, right? So this proves the surjectivity. Why this is true? Because this is trivial, right? Because phi of S, let me just write phi of S restricted on VP by the property, by the commutative diagram is the same as phi of S when S restricted to VP. And this is just T, right? Sorry, it's just S, it's just SP, so it's T restricted to V on VP, right? Because these guys SP. So T restricted on VP. Sorry, it's T restricted on VP. Okay, because this is SP. Okay, so this tells you that phi of S and T are the same on each cover, right? On each open set on each open set VP, right? Because their restriction phi of S restricted to VP the same as T restricted to VP are same on each open set P, or each open set VP. Okay, so by the gluing property, so in this video, so we use two gluing property. First one we use gluing property to find S, and the another one is we find gluing property for T. Okay, so by the gluing property, phi of S must be the same, or the sheaf property phi of S must be the same as T. Okay, so this proof is beautiful that you start from the local one and to find local one, and you prove that the intersection is good. Then you find a global one by sheaf properties. Then you prove this is surjectivity. Okay, so this proves the two important thing. And once we have this foundation, then next video we go to about sheafification. So everything should be easy since we already have all these tools, all these results. That see you guys next videos.